Thank you very much, Ildar, for the introduction. Right, so actually I will probably almost skip this slide then, that's been already told. I'm at Imperial, we have the Dyson Robotics Lab, we have some additional activities to the ones funded by Dyson, but quite a large portion of what we're doing is actually funded by Dyson. Andy Davison and me kind of leading the research there. Okay, so today I'm going to talk about spatial perception for mobile robots. So let me start with this slide here, and maybe just to get a bit of a grasp at what people are doing. So how many of you are sort of in the field of computer vision? Okay, how many of you would consider yourselves roboticists? Okay, all right, good. So obviously some of the things I will be saying will be somewhat repetition for some of you, so bear with me. So all I'm going to talk about is going to be somewhat in this context of a real-time control loop that is running on board a mobile robot, right? So this is the kind of typical breakdown of the modules of what's going on. The robot will sense stuff from the external world, will kind of process that in some form of a perception module. This will then be fed to an important module that I'm going to talk about quite a bit today, which is around state estimation and mapping, where you may combine that also with some internal sensing. You come up with a plan of where the robot is, what the environment looks like, and then that's where you can start planning. You can start actually have some kind of higher level cognition in there. But finally, you'll have to send actual controls to some motors in order to actually do something, to act on the actual world, and the whole thing repeats. So just to emphasize a little bit, this is, as I said, a real-time control loop, right? So you have to make sure that whatever you do here is robust. It really always works, right? So these are things that are executed, let's say, maybe 20 to 1,000 hertz. So that really has to always work. You can't just have that break every once in a while. It has to be also efficient for the same reason, right? It's you have a sort of fixed computational time budget to execute these things. But you also need to have the accuracy for a specific task that is necessary in order to complete it. So these are somewhat contradicting requirements, of course, so you have to kind of find a compromise in between those, given also the sensor suite processing hardware that you have. So you have to come up with a solution in this space here of the right sensors, the right processing, given all the constraints that you have. And then obviously it is a lot about designing the right algorithms and the right software in order to do that. So in the talk I'll be emphasizing a couple of things that I think are important if you want to do that, and we have done a lot of research along those lines. One is that typically one sensor alone is not enough if you want to have an actual robotics application. So very often we have complementary sensors that we want to fuse with each other in order to achieve the kind of robustness that we need. What I want to also emphasize is that dense mapping is really key for planning. So that's kind of why we have been driving our research into that direction, to make sure that we have really kind of dense understanding of the geometry around robots. And then finally, and I think that's somewhat probably a new topic that we'll be touching on a little bit, is that now with things like deep learning that have really revolutionized computer vision, we are finally in a position where we can really connect together geometry, our geometric maps, with a semantic understanding to drive new applications that are going to be much more capable, hopefully. Okay, so let me have a little bit of a high-level overview of what ideally we would like to be. What we'd like to do. So the problem formulation is put in this probabilistic SLAM context, simultaneous localization and mapping context, is that we have measurements, I'll call them Z throughout the talk, that we model as samples from a distribution, right? So we assume that we can somehow model the probabilistic distribution of how these measurements are generated. So we model that as a distribution of the measurements given the states x. The states x are the ones that we would like to find, position, but could also be the map, for instance. Depends on the problem. So x is the thing we want to find, z are the measurements that we are given, and we need to find this, we need to model this distribution. Right, and so now we can actually formulate this problem in a relatively clean way, I find. We can say, okay, all we need to do is we have to find the variables x that best explain all the measurements, given this distribution that we've modeled, right? So this sounds like, you know, the right thing to do. It's called maximum likelihood estimation. We can slightly extend it and also consider a prior distribution of those variables if we have some additional knowledge about what those variables might be. So this could be, for instance, a regularization term for our map, some kind of continuity that we know from the environment. And then this is called maximum a posteriori estimation. If we consider not only these measurement likelihood functions, but also some kind of prior that we know somehow, we may have learned that, right? Okay, so this sounds like, I mean, theoretically, of course, the right thing to do. In practice, it is a bit tricky to do that. So our research here is really about how to try to get as close as possible to this ideal world. And there's a lot of steps needed. I mean, first of all, we have to do something, just deciding what are actually those representations, what are those x, what do we even need to estimate, how do we want to represent it. There's a lot around that in the very beginning that determines what the research actually consists of. Also, how do you model these functions, these probability functions, right? I mean, there's a lot of assumptions that we will need to make here. We don't know this function, we can estimate it, we can approximate it. And then there's a whole lot of other approximations that we will need to make in order to then actually solve this problem of kind of maximizing this joint probability function, if you want. You can do, for instance, iterative optimization. You can pose it as a rather kind of a filtering problem. There's a lot of choices there. And also something that often I think is somewhat overlooked is ways about how to bootstrap your problem, how to have an initial guess, how to associate data. Specifically in vision, this is very crucial, right? You have to, that's a very first step, to associate observations over time and you move. The way you do that is very much going to determine the success sort of your approach. So I'll be talking about some examples of how to do this. Always we kind of start with ideally doing this, but you will see in the examples that often we can't. But I think it's just important that at least we are aware what are the kind of simplifications that we assume. Rather than doing it the other way around and kind of bottom up, build up some system that we don't really understand and then it might work or might not. I think it's always good to put it into the context of this ideal world of what are we actually ideally trying to do and then simplify from there. Okay, so here's an example of a state representation of a state vector that we are trying to estimate. This is a drone that we have at the lab. What we are trying to do here is we're trying to estimate position and orientation of the drone with respect to some world frame that is static, fixed to the Earth. So this is position and orientation quaternion. Then we also include the velocity, in this case represented in the world frame here. So with respect to this guy that we represent the velocity. And then there's a couple of more terms here. In fact, you know, this is now one of those modeling choices that I mentioned before that we might take, is actually the position orientations of the cameras relative to the inertial measurement unit which sits here. So this is a kind of online calibration of the poses of the camera that we can do in this case. Because, you know, these things, they might move a little bit. You might have temperature changes and little changes, so you might want to do that. again, this depends on the application, the accuracy you want, the computational budget you have, how well you have designed this system. These are all factors to consider when you decide on whether or not you want to do that. And then finally, we have also some more internal kind of states. In this case, it is biases, time-varying biases of the accelerometers that measure the acceleration, and the gyros, which measure the rotation rates here in the inertial measurement unit. And these are MEMS sensors. They are not perfect. They will have biases, and unfortunately, these biases, these kind of errors, are going to vary over time. This is why they are included here in this overall state vector. So you see, this can be a combination of somewhat physical robot states that you are actually interested in order to then control the robot, but also some extrinsics of your sensing system, so relative poses, as well as intrinsics that you don't really care about, really, neither of these, right? But you have to, maybe depending on the application, include them in the estimation problem. Okay, so let's talk a little bit about also representation of the environment, and I'm just quickly skipping through this just to show you that there's really a lot of choice here again as well, right? So for instance, we can model our environment in some kind of depth maps. So you have keyframes, and then you store the distance to things in let's say a dense way, or some sort of a semi-dense way, of where you only store that those distance values along edges where you have more information about it. So this is a kind of a 2.5D representation. You lose some information in terms of where things are occluded, but it's actually quite handy. It's quite easy to handle. So maybe this is actually a quite popular representation, right? If you want to go somewhat more principled, people have been using more volumetric, dense formulations of the world, so things like truncated sign distance functions that can then implicitly represent surfaces in the world. But that's coming at quite some overheads in terms of storage and computation. So you will always have these kind of trade-offs again. Then of course there are things like meshes that can really flexibly model the world in principle. You can always represent everything sort of with meshes, but they're also a bit difficult to handle, right? When you go around, you discover new surfaces, you realize how they are, all of a sudden they need to be split or merged and refined. So that can be quite tricky to actually do the bookkeeping around these formulations. And then down here we have again, two formulations that are easier to handle, but maybe a bit more difficult to interpret. Of course, just things like point clouds, where points are just individual. They're just sitting around in the world. This is a kind of a sparse representation of the environment with sparse point cloud. That's a more dense one, where in fact not only do we represent points, this is a circle representation where you have, for every point, you have a physical extent. You actually use a kind of a disk with a radius and a normal direction and a color, so you can sort of encode more information, but you don't have any connectivity here again, right? This is the thing you lose, as opposed to, for instance, a mesh where you can kind of move along the surface. Here you just have a ton of circles that you don't know how they are related to each other. So again, just to emphasize, and that's also not a complete list here, but we have a lot of choice, and you will see a couple of examples later on. So if we are talking now about how to formulate this measurement likelihood function, that's the next step, sort of from the first slide, right, of things we have to do. So this is probably somewhat repetition for those of you who are working in computer vision, but let's not forget, so what the actual camera does is usually you can just model it in some simplified way, as you have a camera center, you think of an image plane in front of that camera, and then you project stuff from the 3D world onto that image plane. So you just follow the rays, you project them onto the image plane that is kind of at the distance f focal length in front of the camera. So that's the usual model that we use, even though we know that sort of internally in the camera things are a bit more complicated, but that's the way to think about it. And of course, through this projection, actually, you know, we don't know how big things are if we just have one observation. We know that the same tree here, closer to the camera, smaller, will produce exactly the same image. So we lose this information about scale. And this is actually an important one in a robotics context, right? So we need to think about ways of bringing that back. So talking about this idea of sensor fusion, a popular one is to fuse visual information with inertial measurements. Introduced a little bit the inertial measurement unit just before. And so here's the idea of why we are trying to do that. I mean, I mentioned at the beginning that sensor fusion is important, that in order to get the kind of robustness and actually also more accuracy. And here's the intuition about it. So in fact, if you think about two views here of the same thing, right? What the vision tells us, in this case, sparse vision, a sparse formulation of the whole thing, it tells us really how the camera has moved in terms of pose. So what is the relative pose in between those views? And as a kind of side result of that, we get out also the 3D points here about where they are placed in the world, right? So first of all, we have to find these associations. We have to find which are the points that correspond to each other, and then we can solve this problem about how the camera has moved in space. So this is the camera tells us purely something about space, about how the camera has moved. It doesn't tell us anything about time, right? And also, don't forget here, we don't have the scale, right? So it's only 5 degrees of freedom that we can solve. We know how the orientation has changed, we know the direction of motion, but we don't know in meters how much the camera has actually moved and how far away those points are. Now, the inertial measurement unit tells us something which is really complementary to that. It tells us how this combination of the two has moved in time. It tells us a lot, quite accurately actually, about the short term, what this motion was. It doesn't tell us much about the long term. If you move for a long time, you cannot simply integrate the accelerations here and the rotation rates and think you will come up with a sensible result. But on the short term, it tells us quite a lot about how this thing has moved. So it's, of course, now it's not quite clear how to combine the two together. We had the visual observation model that I've talked about before. You can say, okay, the 3D points project into the 2D plane, and then you can assume some noise around that. Now, how do we deal with the inertial measurement unit? Not quite clear. So I'll spend just a little bit of time explaining this one. So in fact, you can go back to kinematics and formulate a continuous time differential equation about what's going on. So the first one, let's start with the first one, that's the easiest bit. It basically tells us that if we take the time derivative here, the dot is a time derivative of the position of our robot with respect to the world frame here, then this should be equivalent to the velocity vector represented in the world frame. We can do a similar thing. I'm not going to explain the very details of it, but it's essentially a similar thing for the orientation. We can say the orientation quaternion here, it's somehow a function of, a nonlinear function actually, of the orientation as well as of, and that's the important bit here, the rotation rates that our inertial measurement unit gives us. So these are the rotation rates, and the rotation rates are measured in the IMU coordinate frame, right? If you move it around, then this frame moves around. And another thing to consider here is that these measurements won't be perfect, so we consider them to be noises. W here is a Gaussian white noise term, as well as that there's a bias of the gyros that we need to deduct in order to get the correct measurement, if you want, right? This makes it a stochastic differential equation essentially now, because we have this noise term. And also we have now later on to think about how this bias here will change, how we can get that one. And then the final one here is telling us, okay, the time derivative of the velocity represented in the world frame, actually this should be something like acceleration, right? And acceleration is a thing that we measure, so we do the same thing here again. we measure the acceleration here, we measure that in the IMU frame, and we have to consider noise as well as a bias of these accelerations that we measure. And now I told you, right, that this is measured in the coordinates of the inertial measurement, so we have to transform that via this rotation matrix here into the world frame, and then things are correct, right? Then we have actually acceleration in the world frame that should be equivalent to the time derivative of the velocity in the world frame. And what we also have to include here is acceleration due to gravity, right? So this is actually an interesting one because it gives us now all of a sudden some form of an absolute direction, at least with respect to the gravity vector. That is the thing that makes it also interesting when combining it with vision. All of a sudden we get this sense for what is down, and of course that's the thing that we all know always, right? When we essentially do the same thing of sensor fusion of accelerations and rotation rates and vision, that's the thing that gives us. We always know because of gravity what's down. What we don't know though is where is north. If I ask you, you don't really know, right? So there's some ambiguity there. But we always know as an absolute direction, we know the down direction. So finally, this is a model here for how these biases evolve over time, and that's some modeling choice now. What's up here is actually what physics, what kinematics tell us, and this is a modeling choice. It essentially says, well, we can just model these biases as Brownian motion. They just, they vary over time a little bit, so we can somewhat sloppily say here the time derivative of the biases are equivalent to a Gaussian white noise process, and is very similar for the accelerometer bias as well. So now we have a probabilistic model also for the inertial measurement unit. But as I told you before, this is now a temporal model, right? This is a differential equation in time. Okay, so now we can think about how in practice to actually solve this estimation problem. And just repeating a little bit what I said in the beginning, we want to estimate those variables x, states, position, orientation, and so on, as well as the map. And we have measurements. We model them as independent measurements. Z for given states. So we want to find this most likely explanation. So in other words, we want to find the x that maximizes this posterior distribution of our variables given all the measurements. And we said at least partly these are independent measurements. So we can formulate this whole posterior this whole distribution as a giant product. So what I've put here is I've said the posterior distribution P of x given all the measurements is proportional to P of z given x. So P of z given x, that's the thing that we have modeled actually, right? And z, the measurements we actually have. So that's really the thing we want here. But this is not quite trivial about why these should be proportional. This is essentially the application of Bayes' theorem that I've put here. That says they are proportional. And then we can do maximum likelihood estimation. And a similar thing, if we have a prior distribution for x, then we get the product of all the p of z given x times the prior for the variables x. So we get another giant product, but we have additionally here a factor of the prior distribution of x. So this is really the only difference between maximum likelihood and maximum a posteriori. So this is the thing we want to do. Now we still don't know what these distributions actually are. So very often we can assume, or we just assume that measurements are somehow Gaussian distributed. So if we do that, if we now assume that these measurement likelihood functions here can be modeled with Gaussians, normal distributions, with the mean and the covariance. Similarly for a prior, if we have one, then actually this thing becomes now tractable, because we said we wanted to find the x that maximizes this posterior distribution. Now we do a trick, And rather than saying we maximize the posterior distribution, we can also say we minimize the logarithm of, the negative logarithm of this posterior distribution. And we'll see in a second why. Because now actually when we plug in the normal distribution, this is this giant exponential function here. We can just plug it in now. We just say, okay, we plug in the normal distribution for this guy. We get this exponential distribution here. And now the nice thing is that we have a product of exponentials, and because we take the logarithm of that, we are simply left with a sum of what's in the exponent here. And so the exponent here is very conveniently the actual measurement that we have minus the nonlinear function of the state that generates that measurement, weighted with the inverse of the covariance, and then the square of that whole thing. So actually it conveniently transforms our quite kind of abstract sounding problem. It conveniently transforms that into a nonlinear least squares problem. So we just have to minimize this cost function, and then that's actually equivalent to maximizing this posterior distribution here for the variables x that we want to estimate. So we have now a probabilistic interpretation that if we formulate things as a least squares problem, is actually equivalent to assuming Gaussian distributions behind it. So that's nice. I mean, of course, not everything will be Gaussian distribution in practice, but actually turns out for quite a few things this is very helpful. Okay, so what we're left with still, of course, we have to find this nonlinear mapping of the states into the space of the measurement, and then we can compare actual measurements with those measurement functions, and we can try and minimize all of that. And very similar, I'm not going to the details here, very similar, we can actually do the same thing for maximum a posteriori. You just have an additional part of the sum here which considers the prior for the states x, and it's weighted with the inverse covariance of that prior. So what does that now mean for, let's say, vision only? For vision only, the problem is, okay, we're trying to find 3D points. In this case, world representation is 3D point cloud, at least in one formulation. And we have cameras that observe these points. So we have measurements here of those 3D points. And the camera moves. So we have more observations of the same points, hopefully. Some of them are going to be the same, otherwise we can't do much. So we have, again, 2D points, 2D measurements of those 3D points. So this is very much like the example I've shown you in slide, 1 or 2 slides before, where you see the same points observed in successive views. So now what we're trying to do is we're trying to find the poses or the relative pose of how this camera has moved from here to here, and where are the 3D positions of these points. So this is really the bundle adjustment problem that we can now formulate. And I told you, if we assume Gaussian likelihood functions, we assume a normal distribution of those for those 2D detections around the actual projections, then we can formulate this as a least squares problem. So we just have to say, I have my actual detection here, and then I compare that to the projection of my 3D point onto the image plane, and I'm trying to minimize those. I'm trying to find the best explanation. That's really what it is for these points. So skipping somewhat the maths behind that, but I hope you got the intuition of what we're trying to do here. This is a factor graph representation of what this is actually doing. Here you see the vision only problem. In essence, everything that's round is the variables that we are trying to estimate. So in this case, landmarks as well as poses over time. So the robot moves, captures new images at different poses, and at the same time we want to estimate those landmarks here. And now the measurements that connected to are essentially connections between these landmarks and the poses, always kind of one pose at a time. So here we have these key point measurements, the green boxes. So this is now our completely spatial model of what's happening if we consider only vision. Now if we consider also inertial measurements, then things change, right? I told you before, then we have this kind of temporal measurement that connects two poses with respect to each other. That's the accelerations and the rotations that have happened here that give us these connections. And in fact, we have to also consider the velocity as well as the biases, right? That's what I've shown before in this differential equation. So we have to augment the state. We have to do a little bit more work here. We have to estimate a little bit more because these are also going to be correlated over time. Now, the nice thing about the probabilistic model is that if we can formulate these measurements, the things in the green boxes here as kind of Gaussian distributed measurements, then we can directly put together a global cost function to minimize. Also in this case, where we have very much heterogeneous measurements, right? One coming from the IMU, the other one's coming from vision. How do they go together? Well, they all go together due to the introduction of this probabilistic formulation. So all we have to do is we have to weigh the individual error terms with the inverses of the covariance matrices that we have found. So in essence, here they have the visual part. This is the reprojection error across all the poses over time of all the landmarks that we are trying to estimate, all the measurements in the different cameras. And on that side here is the IMU error that connect two successive states. I haven't really talked about how to do this exactly. I'm just going to touch a little bit on that in this one, because there's a little bit of trickery here. In fact, you have to think about it that way. You have in time, right? We have a camera, an image taken here, and then you have a bunch of IMU measurements, and then we have the next image. So how does this now all work out? Well, in fact, what you can do, and I'll skip the math here, but what you can do is essentially you can integrate these measurements, accelerations and rotation rates, from one camera frame to the next, and then you can compare sort of this predicted state with the actual estimate that you have at this point. And because we have introduced those noise terms, well, the integration of the noise essentially gives you the right covariance matrix that is used for the weighting. Now, the problem with this formulation somewhat is, what do you do over time? The problem will just grow, will get bigger and bigger. This is a batch formulation. It's estimating the whole robot trajectory from the start. And that's not very practical very soon. That's why people have thought about filtering methods of, getting rid of the old states and only ever estimating the current state of the robot. So here is how you can transform this batch formulation that I've now introduced. We know this is a very clean formulation. It's a probabilistic formulation. How you can transform that into something more useful that actually bounds the complexity. And I cannot explain all the details too much, but essentially what you're doing is you limit the number of camera frames in the past that you're trying to keep and want to keep optimizing and estimating, because otherwise it's untractable, right? And you can kind of try to do that in a smart way, that you can even keep very old frames, very old positions, and then you can estimate the motion relative to those really quite old poses that you have estimated. And this helps reducing drift, because you can always reference yourself to something you have observed way in the past. So we just keep this as a constant kind of a window of, this is the same kind of graphics of poses in the past, as well as speed and bias estimates. And the mechanism behind that is used to do that is a concept called marginalization. It's really the same thing as is done in an extended Kalman filter, where you eliminate out of the optimization system, out of the Gauss-Newton system behind that, you eliminate variables and you won't touch them again. So I'll skip the maths about that, but just to give you some intuition, it essentially just says you don't care anymore about some of the states in the past, because you simply can't. You can't consider all of them as your robot moves along. So I think that was kind of the theoretical part. So let me now show how this works in practice. This is a system we have actually released that does exactly what I've just explained, this kind of probabilistic fusion. So you can see on the left, this is actually a drone that's flying around. You can see how it relates key points from the live video to key points in a past frame, a past key frame. So you can see these data associations here. This is really the kind of bootstrapping part. You can see here what's actually happening. And on the right side, you see what's happening in terms of estimation backend. You can see the yellow line is the trajectory of the robot as it moves around. And the points are the estimated 3D landmarks, sparse point cloud. That needs to be estimated as well. And now the nice thing is that, because of the fusion of these complementary sensors, you actually get a lot of robustness, even if you move the robot very fast, even if the drone here flies into very dark areas. You see there's only quite a few points now that can be observed and matched. And if you try to do that with vision only, it's quite likely to break, or at least to be very inaccurate. So that's where you start now benefiting from this whole exercise of sensor fusion. And now that the thing comes back, in fact, what we haven't done here yet is having some form of loop closure, so it doesn't detect it's actually coming back to the same point. It is a quite stupid system. It just estimates incremental motion if you want. But we can now actually see that even though it has no notion about coming back to the same place, the estimate of where it comes back to is actually quite close of the starting point. So that you can observe the drift here. It's actually really quite small. And this is a framework you can download and try it yourself. A little bit of a health warning. It is a bit tricky to really have a very nicely synchronized and calibrated system with inertial sensing and camera or two. Okay, and now of course also we're going to put that onto an actual, into the actual real-time control loop. So here's an example of what we did. I'll just stop that here for a little bit. We have integrated the whole system in our drone. In this case we have a NUC here that does the processing, so does all of that, what I've shown before on board here. And then it has this real sense camera, which is an RGB depth camera with an integrated IMU. So this comes kind of out of the box. That's the nice thing about it. Then that's connected to the computer here, and we are running this visual inertial odometry that I've explained before. Obviously, this is outdoors. We could actually just use GPS and more standard stuff, but we wanted this to work always, also indoors. And we are now thus showcasing the whole thing without GPS, actually. Also, the nice thing, actually, this is a quite cheap drone, really. This is all components that you can buy off the shelf, and that don't cost the world. So I think the whole thing is below £1,000, actually. Right. So I'll restart the video. What we're trying to do here is this was for the Mohammed bin Zayed robotics challenge in Abu Dhabi earlier this year. We're trying to land on a moving platform. So not only do we have to estimate the global pose of the drone and then control it, in this case it's a real-time model predictive control loop that we are running, but we also have to estimate the position and orientation of this target is supposed to land on. So we have additionally a downward-looking camera and an additional kind of a filter for the position of this guy, and then we can try and follow it with an accurate model predictive control loop and land on it. Okay, this is an application of that. Now I mentioned in the beginning, now we can do quite a few things, right? But this actually has still assumed that there's a lot of free space. There's not really much of a useful map in this case that the robot has. It has a couple of landmarks it estimates, but it's mostly useful for localization, not really as much for navigating around that stuff. So what we really like to do is we would like to have some kind of a dense representation of the environment. So actually, I think through the introduction of depth cameras like the Kinect or so on, that this has become really popular and actually more and more easy to do. So we can use depth frames and put them together into a dense map. In fact, you can also do it with monocular cameras, but if you do it with monocular cameras, there's some additional steps. So a typical dense SLAM algorithm, though, what it actually does, things like, let's say, Kinect Fusion, you may have heard about that or not, but what it essentially does is you split things up into two steps. You have first a tracking step. You try to align the RGB and depth image towards a previous one or towards some kind of a model that you have built up. So you solve for the pose only, 6 degrees of freedom, solve for the pose. And then once you have found the pose, you put new data, new depth information and new color information into that map, and you repeat. So, of course, this is now pretty much a departure from this nice probabilistic formulation, right? Because you assume that these are sort of independent things, and you don't jointly optimize the 3D structure and how the camera has moved. So it's not optimal in that sense. It's not. So let's keep that in mind. But it's actually, if you think about it, how would you even do that, right? You would have to optimize the whole dense map as well as the trajectory of the robot. It is kind of becoming untractable. That's why people have turned towards doing something approximate here. So that's relatively straightforward forward to formulate. Now, in the case of only having a monocular camera that moves around, you can still do something in terms of dense mapping. And typically what people do is, well, first you do a tracking step. You align the image with the projected map, optimize for them to match up. Again, this is typically posed as a least squares problem, but holding the map fixed, assuming the map is perfectly known. And then in a second step, you fuse in new data. Now the problem is, of course, we don't have depth directly, but what people usually do is this one here, is you compute the depth map from a previously known pose, and you have a relative pose that you've just estimated. So you've essentially got the virtual stereo camera, if you want, with some baseline in between. You can compute the depth map, and you can fuse that depth into a model. And so here's an example of exactly that that we have done. We are fusing depth from a monocular camera into a global model. Now this is an interesting bit of work, I think, because what we did here was to represent the map with kind of dynamic levels of detail. So what we'd like to do is we would like to have a coarse representation of the map if we are far away. We don't know much, and we know only uncertain information about depth. When we get closer, we want to see more details. So in fact, this is a map representation here that consists of a base height map here, and then some form of a difference map. So I'll just quickly go through that. Now, again, this is a bit of a simplified formulation of how to represent space, right? This is only height map, 2.5D if you want. It's not entirely general, but you can still do quite a lot of things here. So you can see here, that's the live camera. That's the depth maps that are generated from kind of successive views. And then here you can see the global model that we fuse into. And you can see first it starts off with a relatively coarse representation, relatively coarse height map. And then as you spend more time, you get closer, information accumulates, and you know more about the geometry, and you can refine it. You can kind of start reconstructing at a higher level of detail. Okay. So then these details start appearing as you're moving around. And then at the same time here we can of course fuse also brightness information that is coming directly from here, and we get this kind of colored, or in this case black and white, quite nice looking model that we can then use for robotic planning in principle. Okay, I'll skip the rest of this. So let's come back to a problem that I briefly mentioned, but I haven't really talked much about. It's a problem of loop closure. Right, so let's assume now we have a SLAM system that quite accurately estimates how the camera moves from here to here to here to here. At some point you come back to a previously seen place and you're trying to do something. So first of all, you have to actually identify that. There's techniques to do that. I'm not going to talk a lot about it. But let's say then you estimate, well, actually my pose relative to that first frame here is the red one rather than what I previously thought the gray one. So you have this discrepancy and you have to sort of resolve that, right? And again, what people usually do is you formulate this as a nonlinear least squares problem, and you can optimize this whole trajectory. You can try to keep, you know, the difference of 60 transformations between the individual cameras here. You can keep that kind of small, so there's only a little bit of relative change here. And then you have fixed the global kind of discrepancy here, and you have a consistent estimate of everything. So this is something you can do if you're not really doing much with the map, right? Then you can formulate this as what is called a pose graph optimization problem. You have nicely optimized your trajectory now, but what are you actually doing with the map if you have a nice dense map? That's not quite clear, right? So what we have done in this work here, called Elastic Fusion, is rather than posing this as a pose graph problem, we have said, okay, maybe we can directly optimize the map somehow, rather than only the poses of how the camera has moved. So actually we do then SLAM here. We estimate how the camera moves with respect to that dense model. In this case, it's a surface model. And then occasionally when loop closures happen, we elastically deform the map. So we find out, it's where it starts now, right? It's starting to remap the same thing again. It's detected that it's doing that. It's then aligning the two instances of those maps, the new and the old, and it balances this error that it's made across the whole map through elastic deformations. And that ideally keeps the whole map more and more consistent and gets the map more and more accurate as the camera moves around. So here the circle formulation of the environment is actually quite handy to do that. It would be really tricky if you had some kind of volumetric representation or this height map I've introduced before. Like, how do you deform that? That wouldn't be quite clear. But here, if these are individual independent points that are being moved. Okay. Oh. Right. Now the next question is, of course, well, okay, this is now only vision that we have done in Elastic Fusion. How can we bring in inertial measurements? And that's some new work that we are going to present at IROS this year, where actually we included into the tracking problem, we included also the very same inertial measurement term that I've previously introduced. So just a little bit, the tracking part of Elastic Fusion can be represented with a very simple factor graph here, actually. So you just have this measurement term directly off the pose. This is the 3D position and 3D orientation. Only one at a time. You keep the whole map fixed. So the only optimization problem is really for 6 degrees of freedom at the time, position and orientation relative to the map that is held fixed. Now if we also include inertial measurements, we can do that. We still assume the world is perfectly known, the map is fixed. And now we have, again, this temporal term, so we can actually estimate 2 time successive poses. We can estimate them at the same time, and they are connected with IMU measurements. And again, we have to include now speed and bias estimates as well down here. And we can keep a linear prior. We can keep that around, again, through this process of marginalization. So this essentially now becomes something a bit like a Kalman filter that includes visual observations as well as IMU error terms. So we can have more accurate tracking because of that, because again of this mechanism of balancing these two terms. And in fact, we can also slightly change the map deformations. We want to make sure that the map doesn't deform out of the gravity direction, because we have this information now about what's actually down and what not. So we can just augment this cost function for the map deformations a little bit to make sure that things don't get deformed out of the gravity. And yeah, I think I'll skip this video. It just essentially tells us that you get higher accuracy, you get less drift, and you get more robustness again through this process. Because actually, if you ever played around with Elastic Fusion, I don't know if you did, it's really easy to break it. If you just move it a little bit fast, you have not enough overlap from one view to the next. You know, it will break. And with the inclusion of inertial measurements, it's becoming much more robust, much more practical for a robot. So let me now briefly talk about the kind of last element that I've mentioned in the beginning of the talk, which is about semantics. So I've shown this Elastic Fusion system that can produce really quite nice looking, quite useful already geometric maps. You know, these geometric maps can be used for planning, for instance, make sure your robot, your drone, whatever, doesn't bump into things. But it has absolutely no understanding of, well, what this actually is. Right? But you can safely, let's say, fly around your drone, or safely let your vacuum cleaner robot go around here. Has no notion about what it actually sees. So we would like to go towards an annotated map, something like that, which has semantic annotations. You know, it will know this is a bed, this is a window, and this is the wall and the floor. It's actually quite useful to know, right? So that work called Semantic Fusion, it's actually quite a straightforward method of what we're doing here. So this is the output of the system, exactly what I've shown before. Comes up with these annotations, and it really lives in the 3D world. It is not a kind of a traditional 2D semantics annotation that we get. So of course this is using deep learning. This is 2017, right? You have to do deep learning. And I said it was quite simple, and it really is. So we have the stream of images and depth maps that's coming here from the camera, and then we just do Elastic Fusion, as I've explained before. It puts together this map, it does elastic deformations, keeps everything consistent, and at the same time we feed these images into a CNN, and it will give us kind of semantic segmentations that we interpret probabilistically, and we, well, essentially then treat that as a measurement likelihood function for the semantic classes that are being seen. And again, using the camera projection, we can now associate the semantics seen in the 2D image with the semantics of the individual circles. So we can fuse, that's why it's semantic fusion, right? We can fuse this semantics information in the 3D world. And the interesting bit is that, you know, it's not just a one-off thing. You have your 2D semantic segmentation, you project it in the world, and you're done. No, you can actually accumulate evidence from different viewpoints. You know, you may see something from one viewpoint, your CNN is not quite sure about what it is. You see it from a different viewpoint, maybe from closer by, and then you discover it, and you can keep this information around. When you go further away, you just simply don't see stuff anymore, but you can remember, and you come back and you will revisit the whole thing. So that's the nice thing of including the whole 2D only segmentation in the 3D world. So I can actually show you some results here. I mean, of course, what we actually want for robotics is really the kind of 3D and annotated world. But what's interesting specifically for computer vision researchers is that actually, because of this, well, let's say a spatial context of fusing from different views, you actually get the benefit in terms of just simply the 2D semantic predictions. So if you can pretty much use any CNN, and if you can run some kind of dense LAM system in the background, what this says here is the SF is always the semantic fusion. You get an increase of well, class average or pixel average accuracy. So this is using just pure 2D semantic segmentations, using our RGB-D inputs. And then if you combine it with the SLAM system, you get an increase of like, 3-4 percentage points in average. Or we can also combine that with some CRF to do some regularization in the map, then you get a little bit more even. And you may say this is only 3 or 4 percentage points, but in the computer vision community is actually huge, right? This is and the thing is, it's not just for something very specific that we do. You can pretty much use any CNN, and you can expect to get a boost. If you start with a really good one already, you can expect to get a boost if you combine that with a SLAM system. Of course, not always you can do that, right? You don't always have the computer vision community, you don't always have time series that let you do this association of data. But that's, we thought was an interesting finding, kind of in addition to our goal of trying to do a semantically segmented 3D map. So here is just one slide of something I wanted to quickly announce as well. You may have seen that. We have also worked a lot with rendering, with synthetically generating stuff through simulation. And in fact, this is a quite big data set, 5 million of photorealistic images that we have generated sort of with random placement of objects in random layouts. And then we can render the scene, and we can give the ground truth depth as well as the ground truth instances and semantic classes, and even optical flow. So this is our actual sequences in this case, and not individual images, again, to have this kind of SLAM context. So you have quite a lot of ground truth here, and you can of course then use that to train deep learning models, or to verify even SLAM systems and so on. So we've actually seen that having really a lot of synthetic images combined with still real-world examples as well gives us a boost in performance compared to only using real images. So it can be really something interesting that we need to further investigate. So that's coming out at ICCV, but you can already, if you want, you can download this system. By the way, also Elastic Fusion has already been released. We're trying to release Semantic Fusion quite soon as well. And so this is a final one I wanted to show. This is along the lines of exploring novel sensors. This is sort of exotic, maybe a little bit. What we're doing here is we've used an event camera. Maybe I can quickly stop. Who has heard of an event camera? Okay, so just a couple, so I'll stop that here just for a little bit. So an event camera is a very much different paradigm of how you sense. A traditional camera will give you over time, will give you sort of snapshots of a moving scene here in this case, right? One snapshot at a time, one image at a time. Now the event camera reports change. It will only report change, but it will report the change with very high temporal accuracy. So you get these little bits of information. In fact, every pixel independently monitors whether or not it goes darker or brighter, and then it will fire an event with a very accurate kind of microsecond timestamp whenever something has changed in here, right? And these pixels are independent, and they will actually they will fire whenever the brightness has gone above or below a threshold. In fact, a factor. So you get as a benefit from this. Sorry, that's not what I wanted. You get this high temporal accuracy, so it can, in principle, much better deal with otherwise problems like motion blur. Also, there's no such problem as the dynamic range of the whole scene. You don't have to settle for either a long or a short exposure, because every pixel is independent. So these are, in principle, benefits. And also, when nothing is moving, you don't get any events. You get this quite sparse stream of events, ideally. But of course, it's now incredibly difficult to do anything with it. And I think that's why these cameras haven't really taken off so far. is that you don't even have an understanding of what the image looks like underneath. So what we are doing here is we are trying to reconstruct the scene as well as the motion of the camera. And has been kind of the first work that did that, and now there's a couple of more. So what we're trying to do is, this is kind of the input events that are coming, that we accumulated here over some time for visualization. But what we're trying to do is we're trying to reconstruct, you can see that in a bit, trying to reconstruct the gradient image. So this is a kind of color-coded gradient image here, as well as the intensity. So once you have the gradient image, you can actually do some Poisson reconstruction on a GPU to upgrade the gradients into intensities. And it's a keyframe representation, right? It's a kind of a semi-dense keyframe. And then we include the depth as well. So we're kind of individually estimating these things. Unfortunately, we can't, as we would like to do ideally, jointly estimate all of these things. This would again be too much complexity. So we have to kind of assume independence between those. So we have gradient, and we have the depth, and then of course the 60 pose of the camera that are kind of alternated in their estimation. So here's a couple of more results. Of course, you have to now move the camera, otherwise you can't do anything. That's definitely also a disadvantage. But you know, if you have something actually quite fast moving, you don't suffer from motion blur. So you can see the kind of color-coded depth in these individual scenes, that it starts appearing once you move long enough. And we have just done a little bit of work to put that together into a keyframe SLAM system. So you start with one keyframe that you estimate, and then once the overlap kind of falls below a threshold, you can insert a new keyframe and keep going with the estimation problem. So that's basically what you can see here. It kind of spawns a new keyframe every once in a while. So that's quite preliminary work in this space of new sensing. I think we shouldn't forget about that part. It's, you know, it's everything. It's processing, algorithms, but also sensors that we should consider. Okay, I think I'll stop here. Thanks a lot, and yeah, I'm happy to take some questions.
Thank you, Stefan.